This lecture is again continuation of the previous lecture where we were talking about convolutional neural networks, and we went through like all the basics which are required, the basic fundamental operation which is used for convolutional neural network. We try to understand like what are the parameters which are being learned in this convolutional neural networks. And the last segment of this lecture is a case study on AlexNet, which is like one of the first deep learning CNN model, which was used, which actually showed like very promising results on ImageNet data set. So we'll go through that architecture, and then I think the following lecture we have is part of that we'll try to cover today. So in that lecture we'll learn about how we learn these filters or how we learn these weights when we train these models on large scale data sets. Okay. So let's start with this case study. The name of this network is AlexNet, and this is the architecture which you have already seen in the class. I think we discussed this when we were doing the introduction for CNNs. And let me quickly go through this. This is your input image, and the resolution is 2 to 4, 2 to 4. That's like the X and Y of the image. And in fact, this is a typo. It should be 2 to 7, 2 to 7. And I have directly took like this image from the original paper, and there itself it was a typo. So don't worry about that. Then 3 is like the number of channels you have in the RGB image. So the first layer is the convolution layer, and all these cuboids over here, which are shown, these are the activation maps, or you can say like the intermediate activation maps in the network. So the actual layers are not shown here. What is being shown in the architecture is just the volume, or you can say like the data points which are flowing in the network. The first cuboid is the image. Okay, so these are pixel values. Again, this is like the output of the first convolution layer. So these are all the activation feature maps. And again, this is like the output of the second convolution layer, and so on and so forth. Okay, so all these are activation maps shown, but how to get those activation maps will have intermediate layers. For example, we have a convolution layer here, we have a max pooling layer, again a max pooling layer, and there will be some convolution layer in between as well. And at the end, you have like a feature volume which is 13 cross 13, and we have like 256 different channels, which is also like the depth of the feature map. And eventually we try to compress it into a single dimensional feature vector. And after that, we have these dense layers, which is just the neural networks, like the fully connected layers. Okay, so 2 of these. And then the final one is the prediction layer, or you can also say like the output layer of the network, which predicts 1,000 different values. Right. So until this point, all of this is like a convolutional operation. And after this is like the neural network, the fully connected operation, which we discussed, I think, in the previous lecture. And okay, so that's like the overall architecture. Input, as I said, is 2 to 7, 2 to 7 by 3. That's the input image. In total, we have 5 convolutional layers. All right, 1, 2, 3, 4, and 5. And these volumes are output of those convolution layers. And convolution layers, is nothing but like set of kernels. So to define a convolution layer, you should know what is the size of a kernel and how many such kernels you want. We have 3 dense layers. Okay, 1, 2, and 3. Third one is the final one. And finally, the output is 1,000 dimensional feature vector, because we have 1,000 different classes. So we want a 1,000-way classifier. And what will happen is each of those 1,000 values is actually corresponding to one class label. And if that value is high, it means that the network is predicting like that particular class. Okay? And all the other values should be low in that case. And these are just the terminologies which we used. So green is for convolution layers here. You can see like we have 5 different convolution layers. And this orange one is the max pooling layer. We have already studied what max pooling operation is. We also had like norm layers. So this was a different kind of normalization. It was performed to like limit the values of the activations. So we don't use this kind of normalization anymore. So these days we have maybe batch normalization, which we'll cover maybe, I think, in later part of the lecture. Or I think we have already covered this. So this is just norm layer, which is trying to limit the values of the activations. All right. Then these FC1 is like it represents fully connected layers. So you have 3 of those. Okay, so that's the nomenclature. Now let's try to understand what exactly this Conv1 layer is. Okay, so input we know it's 227 by 3. The first convolution layer has 96 different kernels, right? And each of these kernels has a shape of 11 cross 11. So that's indicated here. And these filters will be applied at a stride of 4. So by now you should understand like each of these terms. 96 should be fine, that many filters. This is just the shape of the filter. And stride, you know, like when you move your filter, how many pixels you will skip in between. Now, with all these parameters known, you can usually you can easily use the formula which I showed you in the last lecture to compute what will be the shape of the output activation map. Okay, you can just apply like that formula. You have all these variables here. The other point here to note is it's just saying it's 11 cross 11 filter, but as you know that your filters are like 3-dimensional. So the third dimension here will be 3, so which is not stated here, but in fact the filters will be 11 cross 11 cross 3. Okay, the third part is implicit. Now, if you use like the formula which we already know, you can just put it there, and that will give you number 55, and that's why you have like 55 cross 55 resolution of the output activation map. And the third number, which is like the depth of the activation map, which is 96. This 96, as you know, is coming from the number of kernels we have. So we have 96 different kernels, which means we will get 96 of these activation maps. Okay, so that was the first convolution layer. And similarly, I mean, you can go through like the whole architecture here, and you will be able to understand like how we are going from 224 to 55 or 27 and then to 13 cross 13 to 256. You just need these variables and the equation. Okay, so now the question is, if you're using that many parameters, then how many total parameters or trainable parameters are present in this first convolution layer? And again, which is easy for you, you know that you have 96 different kernels. Each kernel has a shape of 11 cross 11, and you also have a cross 3. So which means that you have that many values to learn in this layer, which represents the number of parameters. You can just multiply those. So it becomes 11 cross 11 cross 3 cross 96, which turns out to be 35,000. Okay, so in your first layer, you have 35,000 parameters. Now let's move on to the next layer, which is max pooling layer here. Okay, so after Conv1, you were getting 55 cross 96. After that, we have this max pooling layer where the filter size was 3 cross 3, and this was applied at a stride of 2. And again, if you apply the same formula here, that will give you the size of the output activation map, which is 27. All right, so that's how you get 27 cross 27. And the depth of the output will be 96. So in fact, the output of the max pooling is not shown here. Okay, so the output will be 27 cross 27 and then 96. And then after that, you will apply the second convolution layer, which is giving you this 27 cross 27 cross 256, which means in the second convolution layer, you might have 256 different kernels. Okay, so I think we had like a pop quiz last time, how many parameters we will have in this layer. So max pooling will have 0 parameters because we are not learning anything there, right? We know the function which can be used to perform that, excuse me, that operation. Okay, so after the max pooling, we have a normalization layer. And again, as I said, we just try to limit the values between certain range. So the size of the activation map should not change. It's just the values in that activation map will change. Okay, so the shape will remain the same. Now that was like the first 3 layers, but at the end, like this is like the full configuration of AlexNet. It's giving you the details of like for every layer, how many kernels you have, what was the size of the kernel, in this case 5 cross 5, and it's also giving you like the parameters, what's the stride, what's the padding. Okay, so all these numbers shown here, these numbers are not parameters of your network. These numbers are hyperparameter of your numbers. So there's a distinction between parameter and hyperparameter. Okay, parameter is something which is learned when you train your network. Okay, so those values in those activation maps, but the numbers which define the architecture, or which defines like the training of your architecture, those numbers are called hyperparameters. So parameters, you have no control, they will be learned during the training, but hyperparameters are something which will have to set even before starting the training. Okay, so all these are hyperparameters. Like how many kernels you have to use, you have to make a judgment. What should be the size of the kernel? Again, you have to make some judgment. Again, all this thing, like what should be the stride and everything. So the architectural details of the network, these are called hyperparameters. Okay. So once you have these hyperparameters, then you know what your network is. I mean, with all these details, you don't need anything else. So irrespective of which deep learning framework you use, so deep learning framework is something like where you can train your models. Okay, so it's some kind of backbone framework which is provided. So irrespective of which framework you're going to use, your network will not change if you use like these set of parameters. Okay, you can use PyTorch, you can use maybe TensorFlow. The architecture is fixed. So now let's quickly look at like the number of parameters we have in each of these layers. The first layer we already saw that we had roughly 35,000 parameters. Similarly for Con2, you can do the computation here. You just multiply 256 by 5 and then by 5. And then you know that the depth of the filters in the second Con layer will be 96. Right? Because the output of the first layer gives you like a depth of 96. So the third dimension is implicit. So if you multiply all those numbers, it will give you around 614K. Similarly, you can keep computing these. So you have these numbers here. Okay. So now one interesting thing to note here is these are the number of parameters which you have in the convolution layer. But as soon as you move to the fully connected layers, so you can see like you have like 4096 neurons here and this one and 1000 in the last one. You can see the number of parameters, it's like a lot. I mean, it's too high if you compare that with the convolution layers. And again, the reason is in the convolution part, we are actually sharing the weights, right, or the kernels across space. But that's not happening when we have these fully connected layers. For each connection between neuron in your input layer to the neuron in the second layer, the next layer, you have a different weight. So that weight is not being shared, and that's causing like a huge jump in the number of parameters which are required to train in these fully connected layers. Right? So you can see like majority of the weights are actually coming from these fully connected layers. Now let's try to understand like what is the data flow in your network and what that data flow looks like. Okay, so again, this is like one sample CNN architecture where we have like different con layers. We have different activations. We have like a cooling in between. And then finally, we have the fully connected layer, which is giving you predictions. So let's try to understand like how the data flows. Your input is, let's say, this image. And then what will happen is in the first convolution layer, you will have some set of filters, right? For example, in AlexNet, we had 96 different filters. In this case, I'm showing you roughly around 10 different filters. And each of this is like the activation map, or like you can say the output of one filter. So when you apply that filter to this image, you get activation map like this. Okay. And again, the second filter, you will get something like this. So all these are output from different filters. And since these filters are learned when you train the model, so each filter will be different. Okay. So, and you can see that like, you know that when you perform filtering, you're just trying to match that filter with the input image, right? And if there is a match, you will get high activation. And you can see here that like at different with different filters, different positions are actually highly active. Okay, so for example, let's focus on the first one. You can see that like the bottom of the car, or you can say like some kind of shadow might be there, right? So that filter is actually is very sensitive to shadows, and therefore like at this region you can see like it's highly active, right? So by the way, the second column over here is after railway activation, which means that all the negative values are clipped and you only keep the positive values. Okay, so positive values means which are active. And here you can see that it's kind of getting highly active when you have like the hood of the car, right, which might be very shiny. So it could be the first filter responds to shadows, the second filter responds to like shiny surfaces, and so on and so forth. Okay, so you can have like a lot of those filters, and you will have these kind of activations. So each filter is responsible for detecting some kind of characteristic from your input image. And then again, these activation maps will go to the next layer. And again, you will get different set of activations. All right. And after each cone, you can select when you apply the ReLU, you are just clipping off the negative values. Pooling operation is nothing. It's just trying to reduce the resolution of your activation maps. So as you go down, you can see like what kind of features this network is trying to recognize. And at the end, what will happen is if a car is present, then that neuron will be very active, which is kind of a result of like detecting all these patterns, right? So all these patterns actually play a role in making the final decision. Okay, so these are like the activation maps inside the network. Now, so that was one part of your CNN. The other interesting part is like, okay, what will the kernels look like? Okay, so again, this is a very I think interesting question, but again, it's an ongoing research, and people are still trying to figure out like how to control these things and how to understand like the learning process in deep learning. So I will give you like a brief overview. It's like not a recent work, but what it tries to do is it tries to understand like what kind of features are being learned by different layers of your network. And the idea is, let's say this is your input image. The initial layers, the first few layers of your network, tries to learn low-level features because those filters are directly operating on your input image. And the filter size is usually very small, 3x3 or 5x5. In AlexNet, it was 11x11. But anyways, that filter actually operates on a very small spatial location. And that's why it's trying to capture like those small, like the low-level features. These could be like very simple shapes. These could be like edges, right? So you can see here that these low-level features will be, maybe it could be like edges in different directions or very primitive shapes. Okay, this is like a kind of a circle. And some of these are also trying to react to like different kind of colors, right? Now, as you move deeper into your network, then if you try to think about this, then what's happening is you are kind of utilizing all these low-level features, right? Because all these features, if they are recognized, they will stack up like in the volume, right? They will go as a depth. And when you apply that kernel in like intermediate layer, that kernel is actually looking at all these activations at once. So then whatever decision it's trying to make, it's trying to make use of like make use of all the activations which are present at that level, which means that at mid level, you will try to like combine these and maybe try to learn some complicated shapes. Okay. And as you go deeper, again, it will be like a combination of those activations. So you will try to learn like more complex shapes. And here you can see that some of these are like very well-known patterns which we observe in our input images. Okay. And finally, we use like these activations to determine which object is present in your input image. Okay, so one last question I have for you is like these networks are called convolutional neural networks. Why don't we call them correlation neural networks? Because the operation which we are doing, it's actually correlation, it's not convolution. Right? The kernels, we are not actually trying to flip them and then perform that element-wise multiplication. We just take those kernels and we just do the correlation operation, which is element-wise multiplication, and then adding those values. Right? And which is fine, you can call them correlation, but it's just a term, so don't worry about that. Even if you call it correlation neural network, I think it will be fine. It won't change anything. The interesting thing is it actually doesn't matter, because the core operation between convolution and correlation, it's the same. As we discussed earlier, the only difference is you have to rotate your filters like twice, maybe in x direction, y direction, and then the operation remains the same. So rotating the filter, it's not a big deal. I mean, it's just like we'll have to write extra piece of code. So instead of correlation, you can also perform convolution operation. It's just it won't be efficient. Just like the rotation will add like some kind of computation overhead, and we don't want that. And at the end, these filters are learned. So the idea is, if the network can learn like filters based on the correlation operation, it can also learn the filters based on the convolution operation. Okay, so at the end, it doesn't matter like whether you call this correlation or convolution.